I'll have one. That's why I got to say, I'm probably going to start.
Alrighty. So, my plan for today, since no one emailed me any questions to review for the exam, I'm assuming you guys are all ready. Or I can come up with a few practice problems while we're sitting here. You'll know on Wednesday, I'm sorry. Yeah, I like to grade them all together. That way, in case there's a catastrophe on one of the questions. Right, because if I grade yours first, I was like, man, these guys all got it wrong. Weird. But if the entire class gets the question wrong, then I'm like, oh, my fault. Then I can fix it. Otherwise, it's your fault. I like that plan. Okay, otherwise it's your fault that you just didn't get the question right. So. Yeah, maybe it's just you guys. Okay, so looking ahead, today we're going to do a little bit of chapter 19, just talking about alpha decay. That'll be the last stuff that's on the exam. Your exam is on Wednesday. Then Friday we'll finish up chapter 19. A week from today we'll review the entire semester. That's it, that's the last class day. And then your final is May 5th at 10:30 in here. So, you guys look a little overwhelmed. Don't be overwhelmed. It'll be fine. It'll be fine. And for the final exam, if you're looking ahead to your final exam schedule, I know some people have already talked to me about it, but if there's a reason that we need to switch up times and dates, just see me after class and we'll make sure we get that all sorted out. I'm not sure I replied to you. Probably didn't. You said a date. Okay. So, because I know some people are going to be traveling and some other people have other exams going on. So, if you need to take it at a time other than May 5th, let me know. All right. Let's see. So we finished off doing isotope review. So one of the 4 categories of radioactive particles we're going to look at. All right, we have 4 types: alpha, beta, gamma, and positron. We'll look at alpha first. Alpha decay occurs when an unstable nucleus emits a particle composed of 2 protons and 2 neutrons. So if I was going to define an alpha particle, thinking back to what we did with isotopes over here, what would be its atomic number? 2, right? Because atomic number means protons. So then what would its mass number be? If I have 2 protons and 2 neutrons. Okay? What element do you know has a mass of 4? So an alpha particle is really a single helium atom. when an alpha particle is emitted, bless you, bless you. All right, so if I emit an alpha particle, I've changed the number of protons. What have I done to the element? How do we define what an element is? Number of protons. So if I've changed the number of protons, what have I done? I've changed the element. It is science. All right, so we're going to describe these as a nuclear equation, right? So we've had ionic equations, we've had molecular equations, we've had net ionic equations. These are going to be nuclear equations, where a nuclear equation describes the fission of the element. So here I have uranium-238. And if it emits 1 helium, what has happened to the mass number? What will have to be the mass number of my product over here? 234. And what will happen to my atomic number? It'll be 90. So then we go to the periodic table. And what is element 90? Does anyone read that? This guy over here, thorium. Okay, let's do another one. All right, so I have radium. It emits an alpha particle. What would be the new mass number for this element? 220. What's its new atomic number? Kind of crazy looking. All right. It's over here, radon. All right, so these nuclear equations, sorry, let me fix this out. Somebody messed around with my camera over the weekend. There we go. All right, so these nuclear equations have some specific lingo that we talk about. These guys over here, the original atom, the atom that we started off the reaction with. We're going to call those the parent nuclide. Obviously, these are alpha particles. But these guys over here the product of decay is called the daughter. Don't read too much into that. So the parent is the atom that we're going to start off with. The daughter is the one that we form. But just like any other type of equation, we have to make sure that we're mass balanced in all these, right? The number of atomic numbers must be equal. The number of, the total mass number has to be equal. All right, questions about my alpha decays? Yeah.
Can more than one alpha particle be in the product? Like, can it be like 8 and 4, do you think?
It wouldn't be in one step.
Okay.
So if we see that, it'll have to be more than one step, but theoretically, yeah, you could pop off more than one. But we always write them just as one step. That this goes to this, pauses, and that can decay further, especially when you get into some of these crazy super radioactive elements. They're going to have multi-step degradations. All right, let me get through I'll tell you where the test line is. There's going to be 2 more types of decay, and then I'll tell you where the test line is. We'll do alpha, beta, and gamma decay, then we'll... Oh, what's going on with my crazy camera today? All right, beta decay occurs when an unstable nucleus emits an electron. So if I'm going to describe a beta particle, which is an electron, what is its mass number going to be? All right, we talked about this, I guess, Wednesday. And then we give it an atomic number of -1, yep. To say that's the opposite. So beta decay produce a beta particle. So, for example, if that is the first half of my reaction, what is the new mass number that I've produced? Okay, the same. If I have 88 on this side, what must be the atomic number on this side so that they're equal? 89. So beta decay does the same thing. It makes a new element, but instead of it does change the number of protons, but changes it to increase it rather than decrease it.
Wait, so why does it increase it?
This size 88.
Yeah.
89 plus minus 1 is 88.
And why is it -1 if that is that negative charge?
It counts equivalent to a negative proton in this sword decay. It's like the antimatter, right? It's the antiproton. Because the idea is that if I've changed the number of electrons for this to still be neutral, I have to increase the number of protons. Some nuclear science is kind of funky in its way of counting. All right, let's do one more of those. All right, so let's say I have arsenic. What would be its mass number of the new particle? And then what would be its new atomic number? Mm-hmm. Alright, so there's 2 different ways we can decay. We can either release a helium atom or we can release an electron. Okay, the last thing we're going to do in this chapter today, and we'll do the rest after our exam, is gamma rays. This is a high energy, short wavelength electromagnetic radiation that's being emitted. So it's technically a gamma ray, not a gamma particle. What am I telling you when it has a 0, 0? How many protons does it have? How much mass does it have? None. Because it's a ray, not a particle. All right, no charge, no mass. So when a gamma ray is emitted, it usually occurs along with the emission of another particle. Right, because a gamma ray by itself wouldn't change the element from one to another. So if I look at my uranium-238 again, if we did our alpha particle emission, we would make that thorium compound. But I could also emit a gamma ray, and it wouldn't affect the overall balance of the equation. The purpose of that?
Yeah.
It is, besides releasing a particle, it's the rest of the energy. Right, so when it breaks down, it has all this energy to give away. Sometimes it gives away as heat, sometimes it gives it away as light, sometimes it gives it away as these gamma rays. So depending on what you want, so if you want to give away as heat, you would use a different combination. If you want to give it away as light, you do something else. If you want to use gamma rays, you do this.
So how would a problem like that be worded?
It would be something like the following reaction, following decay gives off an alpha particle and a gamma ray, which is the correct balanced equation. It's going to be in the multiple choice section because really they're so easy. They're like 1, 2 multiple choice questions. Because they're impossible to make hard. So, alright, so we will stop there with the chapter 19 stuff. That's the stuff that will be on the test. We will finish chapter 19 Friday when we talk about fission, fusion, and half-lives. Oh, coming back to some half-lives. Some T1 halves, some kinetics. Alright, so kind of my thought of what I would do. Let's see what I got. Alright, so are there any types of problems people have a question about in particular? I'll just pick some random ones. Random ones it is. Perfect. Alright, how about right, so let's say you're given the following cell. What would be the balanced net equation for that? All right, so what element is being involved in the oxidation? The aluminum or the copper? Okay, the aluminum is. Have I written that as an oxidation? Okay, so then where do I put the electrons? As a product or a reactant? And how many do I need? All right, so then I have this guy. If I know this was the oxidation, where do I put the electrons for the reduction? Okay, and how many do I need? So then, how do I recombine these so I have no electrons left over? Multiply the top one by what? The bottom one by? So your final answer should be good warm up. Okay, what if at 1500 degrees Celsius, the equilibrium constant for this given reaction, carbon dioxide and hydrogen gas making ethanol, is 1.4 times 10 to the -7th. How would I go about finding delta G0? I would use the equation that relates delta G0 to KEQ. Okay, so I'll start. What comes after that? Negative RT. Okay. Yes, ma'am.
Which ones have log and which ones have, log?
There are no logs. If you use the textbook prefers logs. I don't. That way we use ln for mastering chemistry likes logs too. It's fine. You can use logs, but then you gotta use a different constant. I use ln for everything in both these chapters. That way you never be confused about ln versus log. Everything in these two chapters are natural logs.
There was one, that Nernst equation, is that?
There's two options for the Nernst equations.
Yeah, we went over one in class and then mastering had a totally different.
It's the exact same equation. The difference is I use ln, they use log, and so the numbers have to be different. So you can use either one. Doesn't matter, they get the same answer. I think it's easier if we just use ln's for two chapters straight, rather than being like, oh wait, this is the one equation that uses log. So I use natural logs for everything. But it comes out about the same. All right, what's the trick when I'm using delta G's with temperature? Has to be in Kelvin. Let's see, I think that comes out to. What would the units on this be? Joules per mole. Okay, what if I had this one? So how many seconds are required to deposit 1.32 grams of copper solid using a copper sulfate solution and 0.938 amps? First question you have to figure out is copper what is the charge of copper and copper sulfate? It is 2, it's plus 2. So I want the reaction that does so how many electrons do I need? 2. Okay, so this is the unit conversion run. We're going to start off 1.32 grams because that's what we want. How do I get from grams to moles? Molar mass of copper, 63.55. All right, so now I have 1 mole of copper. How many moles of electrons do I need to make that 1 mole of copper? 2. Okay, then we'll use our Faraday's constant. It's not in coulombs. Then I got to worry about this amps, right? And we said the other day 1 amp is 1 coulomb per second. So then how do I need to use these amps so that the amps cancel out? Put them on the top or on the bottom? What units am I going to be left in? Seconds. Good. All right, what if? So how do I go about figuring out what my question mark is? What's its mass number going to be? $137. Mm-hmm. Then how do I go figuring out its atomic number? Right, so it's 55 on this side. I have a minus 1 over here, so it's be 56. Then how would I figure out what element that is? I'd use my periodic table. What element have I made? Barium. That's really as tricky as those nuclear equations can be. For now. We have some half-life questions coming up on this test. Let's see, what about... what equation do I need to use to figure out? Okay. So what, if I didn't give you delta G, how do I go about figuring that out? Has to be 0, right? Why does it have to be 0? Right, that's the tipping point. If it's negative, it's spontaneous. If it's positive, it's non-spontaneous. So 0 is the point, is the smallest temperature, biggest temperature, I guess, where this would not be true. Then what's the other trick to get this to work out? Right, I'm going to convert these all to joules because it's easier. All right, what other kind of questions do you guys want to go over? Those are G's and H's and...
More of those conversion ones.
Ah, mm-hmm.
Unit conversion.
Okay. Let me see what I got. Okay, just did that one. All right, so what mass of silver can be plated in 33.5 minutes using 8.70 amps from a silver bromide solution? Okay, do you want to start with amps or minutes? Doesn't really matter. Amps is fine. That's fine. All right, how do I turn amps into some sort of time measurement that I can use with these minutes? An amp is equal to a, okay? All right, so then 33 minutes is how many seconds? Should be like 2010. All right, now I'm in coulombs. How do I get out of coulombs into moles? Okay. Yep. All right, how many moles of electrons does this reduction require? One. How did we figure out it's one? Right, so I have silver bromide. Is the bromide doing anything useful in this reaction? No, what do we call those guys? Spectators. So what's the charge going to be in the silver bromide? So how many electrons do I need to go from silver plus 1 to 0? Right. All right.
Should we just assume one electron scenarios like that? Or?
I don't think assuming one would be a good idea. Because, I mean, I could have said mass of iron from iron carbonate. Or carbonate's minus 2, this guy's plus 2. So you may have to, yeah, it'd be 2 electrons. So you may have to refresh yourself a little bit on these counter ions if you don't have them off the top of your head. All right, so it takes 1 mole of electrons for 1 mole of silver. Then what's the last thing you have to do to get out of the moles of silver into a mass? Molar mass. Okay, what else? We could do some multiple choice questions. We could do some.
When you have a voltage cell, when you have like platinum that's not doing anything,
Mm-hmm.
can you just explain that?
Yep, what that is. Yep. So let's say, for example, let's see if I have one of those sitting around. Now I can come up with something. Okay, let's say I have so we did it this way. So write the following line notation. Let's say I have that's an F. I don't think it's an F. So I have iron 2 plus and copper 1. making a copper solid and some iron 3+. Which element is being oxidized? The iron or the copper? Okay, so does that go on the left or the right of my line notation? Okay. Our rule is we always put the solid metal farthest to the left. Do I have any solid iron that I'm making? So I need platinum in that case because there's no metal being made or used. Right, because these two guys have to have a surface to react on. That's what the platinum is. It's a physical surface where they can interact and do some chemistry.
So the other question that we're asking us to write the equation, which would not include the bottom
Right.
ions.
Yeah.
Big oxide.
Yep. So platinum's like a spectator solid. It's not participating. It's just a surface for chemistry to happen. All right, so then the other side of my salt bridge, do I put the ion or the solid first? All right, I got time for probably one more. Yes. Sure. Load the balancing equation base. Let's see what I got. Let's say all right, so I got chlorine and permanganate making chlorine gas and manganese ions. Which one do you want to do first, the chlorine or the permanganate? I'm going to do chlorine first since there's no overwhelming majority on that. Because that's the easier one. All right, is this an oxidation or reduction? Okay. So then where do I put the electrons? Now, first off, what is the issue with my mass balance here? It is not balanced. All right, what do I need to do to my reactant side? Okay. So I have 2 chlorine minuses making 2 chlorine gases. Yes, then I need 2 electrons, right? 1 electron for each chlorine. All right, is that guy done? Okay. All right, looking at my permanganate, what is the oxidation state of the Mn? +7. +7 to +2 is definitely a reduction. So I need some electrons over here. How many electrons do I need to make that reduction? 5. All right, now we need to mess around with its acid base. So, do we want to do water first or some protons? Okay, how many waters do I need over here? If I do 4, okay. I mean, we could do 2 and then add 2 more, but I would just do 4 at once. All right, so now what do I need to do to my reactant side to get that balanced? Okay. All right, but we're in base. So what do I need to do to both sides to balance that out? Okay. All right, so now what have I made over here? Water. How many waters did I make? So what can I do to simplify this reaction? Okay, can I just recombine them right now? No. All right, what do I need to do to my top reaction? Okay. Then what do I need to do my bottom? So now I should have that's everybody. So. I don't know what that pink squiggly is. Nope, that's somehow worse.
For the leftover,
Oh wait, that's not right. That should be 5.
for the leftover,
I don't want to make the guarantee. Because when I say that, then on the test it won't be true, and then you'll be mad. So. All right. Go team. Good luck on your test.